In the second chapter of our presentation, I would like to introduce you into some basic concepts of artificial intelligence. In particular, we will be speaking about some specific models, large language models of the generative artificial intelligence. So it's a subgroup, and I won't be too specific on some technicalities, and also there will be some general introduction only, some basic concepts of the functioning of these language models. So one of the first terms that is useful to know is called tokenization, because the language model doesn't work with words in specific. It converts a text. For example, I created a profile of a student, and this kind of text is then transferred into and is divided into tokens. Generally in English, the tokens are a word like the name of a specific form of a verb, like is a 16-year-old. All that is a word, also a token, but also a full stop or a comma or a question mark is also a token. In other languages that are more complex in their grammar, like for example Latin or some Slavic languages which use more the declinations, also the verb and the words are divided into some chunks. So the tokens are the basic unit of working with text. Then the algorithm converts this text and also the tokens. You can focus on to this lower part. Every token is converted into a specific ID. Every token has its own number. Of course, it depends. Every model has its own system of tokenization. So, as you can see, like the computer doesn't know words in a specific sense. It's not about reasoning in a specific, like a precise sense of the word, like in a philosophical sense or theological, if you want. It's a work of a neural network with data, and specifically with numbers. Of course, we are speaking about computers, of course. So every token has its own ID and number, and that is also then easier to make some mathematical operations with it. Then let's delve into a second term which is important, and it's called word vector. It was introduced some years ago as a type of work or understanding of a concept. So like, let's take a concept or a word like cat. So we have vector would be a sequence of different numbers that indicate a proximity to a certain category. So if it's here 0.6 indicates it's a living being. Maybe if it would be like, if we see here like house is minus 0.8, so like it's not living. But it's not 1 or 0 or minus 1. It's always, it depends on the context, on the use of the word. So if also has a certain relationship, for example, with human person or human realities, or the word human. So cat has a certain affinity. Dog has more. It seems. It depends on the text the language model was trained on. House, a little bit less. Then there is the question of gender, or if it's a part of royalty, like here we have another examples, man, woman, king, queen. So here we can see that the category of being part of royalty, it is pretty much present. Of course, you can see that there is a different number between king and queen. We could interpret all of this. Or there can be also another dimension of being like grammatical categories, like being a verb or being in a plural or not. So, for example, interesting, like houses, okay, it's 0.3. We understand it's mostly not a verb, but it could be used like housing to housing someone, no? Or it could be more verb than any other token or concept here. So this is called the word embedding, and then we can represent these dimensions into a two-dimensional, three-dimensional space where we can see that some concepts are near one to another because they have a similar meaning, or they have a near a use in a similar situations. And there is also a question of proportion, in the sense that man to woman is in a certain sense the same distance and direction as in the visualization space, like king to queen. So there is a certain proportion. It would be much more complicated than that, because the dimensions here we had 7 dimensions, and the large language models, they have tens of thousands of dimensions. Here we can see some of the words with their vectors in a so-called data lake entries. So we can see how every word and conversation has a certain proximity to other concepts. So we can see education as a big term, mental health, there are near to mental health there are some disorders, there is learning, and so we could go and see all the typical conversations. Like, for example, I click randomly on one conversation and we can see, okay, it was a conversation between a chatbot and a human person. Please explain the significance of innovative practical courses for students. And okay, all this conversation, it was recorded, and it defines the word education. So I could go to another conversation. It's basically in English. Many conversations are also in other languages. So you can. There are some situations like here. You are a head teacher of a school. Generate a list of 5. There is then word missing, can be used to a survey to improve the academic performance. Okay, here is a sample of. So you can see this free data lake and also this free GPT-4All program in order to use also artificial intelligence for you. And it's interesting to see how the data is not perfect. It's like the single data is far from perfect, and also the conversations are not always satisfactory. But it is interesting that the amount of data at the end creates a good, a certain kind of balance of the semantic area of a concept. Now the last concept is the concept of a neural network, which is a concept in mathematics, in information technology. It's working on many data. It's a very general model which has a very specific type of functioning. So the input data is not only a text, it could be also a conversion of an image, or meteorological data like temperature and wind speed and everything. So it has different input neurons, and this is a very simple visualization. Normally there are tens of thousands or hundreds of thousands of input neurons, then there are many layers of hidden neurons, and every layer intercepts the data from the previous layer, organizes it, and pushes it forward. So we could imagine in a simple way that at the end the output is in a large language model is always the next word. So when an algorithm like ChatGPT gives you the answer, it doesn't know the final answer when it is giving you all the sequence, because it's working progressively, word per word, token by token. No? So if we want to visualize this kind of working of a neural network, I found a good example of visualization. So let's see this video of, actually it's a very simple neural network that is working on written numbers, and it's recognizing the numbers. So this frontal part would be, let's say this would be a scanner, so with different written numbers, and the language model, it's not a language model, it's a neural network that is recognizing the real number. So it's converting it, and it's giving you the output in the form of a number from 0 to 9. As you can see, there are thousands and thousands of connections between the neurons, and this is a very simple task. It's only recognizing one of 10 numbers. So I think it's a good example to show us the complexity of work with neural networks. And this has also some interesting implications around the functioning. It's not about the technicality and engineering of neural network, but it's about the functioning that also the super engineers, who are the architects of these networks, they don't know actually why the output is like this. So you cannot trace back the algorithm to know why it gave you a certain answer to a certain question. You can only train it a little bit better or worse with different weights, with different texts. You cannot influence the single word that's coming out from a neural network because it's too complex. Let's see some implications of these principles. So, like, what are the lessons we have learned so far? We have to be aware that the work with context is very strong. So if you give a chatbot or a large language model a good context and then a very precise question, you can get a very good and significant result. You have to think about all the information the algorithm could use to give you a good specific answer. So in that sense also these algorithms and LLMs are working good with personalization. That's the first let's say an advantage, and an application also in education. So there are already different applications on AI giving specific personalized feedback on some, for example, an online test. So students, different students with their history and background, that is creating the context. That background and history is creating the context for the answer and for the feedback from a test. So personalization could be a strength of these LLMs. Also translation. It's not only translation from a language to another language, which is very strong because it was trained one model that is not only an English model. Like the data, like 70% more or less, it depends on the model, was trained on English language. But there are also another languages which are present and they are interconnected. So the translation that is produced by a neural network, by an LLM, is always aware of the context of a word. So for example, the DeepL translation is already a neural network translation, which is considering also the context, also ChatGPT, Gemini, and other kind of LLMs. They are also translating with an awareness about the context. So those are tasks that could be there, we can leverage the strength of an LLM. Also, summarization of a big text, division of tasks. When you have a text, we have some criteria, and we have to divide all this text into smaller parts, smaller chunks, and we have some educational objectives. We can list them. We have a specific style on how do we work, for example, in an education, and then we can translate a text to a different context and also divide it. For example, we have 3 lessons. Every lesson is 45 minutes, and this is the objective of the lesson, and this is the content. So the algorithm can work on this type of tasks because it is trained to do so. Also brainstorming ideas, because it was trained on large amount of multilingual data. There are some issues or problems or weaknesses. It's good to understand the functioning of this algorithm, because it gives us the real perception. There is no reasoning, like real human reasoning or intelligence. It's only an inference on large data. So, but it's interesting that it's not a mechanical determinism, in the sense that the model has its own uncertainty. It was trained on such large quantities of data. These data or these information are not stored within the model. The information was only used to train, let's say, the word vectors and the linguistic model. So the training of a model, I have done some fine-tuning and some creation of some components that balance the LLMs. It's more about balancing the neural network. It's not about giving a precise instruction what to say in a specific situation. It's not about the right solution. So we shouldn't expect ourselves to have right solutions and right answers from a basic large language model. We can use large language model with our books, our library. I will show you afterwards how we can do that, and it can extract precise data from a database. But there, the large language model is doing only the operation of searching and providing information. So also the algorithm is made to give you answers. Always. It will always answer in a certain way. It's not bothering itself with truth and good information or better. The main focus is to respond, to remain in conversation. But it's not reasoning about the true meaning of the words. It's only about giving a good answer to the question in a certain context. Also, the problem is that the data is very large, but it's often biased or it's low quality. So like, for example, Facebook chats and posts, and sometimes the information are outdated. So LLMs, lessons learned, work pretty good with context, with translations, with division and systematization of tasks, of texts, summarizing, expanding, giving you examples and brainstorm. There is also the art of using an LLM, a prompt. So in a very basic way, it's important, and you can have better results if you define the AI. Like you have to say, okay, for example, an identity prompt for a Salesian teacher in high school. So before giving questions and answers, you should define the conversation. Okay, who am I? I am a Salesian teacher. These are the values. I am committed to educating with love and respect, and so on, rooted in the values of faith, reason, and loving kindness. Okay. So there is identity prompt. There are contextual prompts. You can always, before doing some questioning, it's good to specify the context. Where are we, like geographically, in which culture, and what's the history? And then when I make some questions or prompts or instructions, I have to be specific. What kind of answer do I want? In which kind of language, academic style, or for what audience? For 15-year-old adolescents in a lesson, or in, I don't know, in high school in mathematics, and we are speaking about this and that. So if you specify how do you want the answer and what are you searching for, if you provide more information, you will get a more relevant answer. So that's a very basic rule of how to do the prompting.